Okay, great. So I'm absolutely thrilled to announce that we have Namrata Roy as our speaker today, who is going to talk about from jets to fountains, how black holes shape galactic gas across cosmic time. And we were chatting about where she is at the moment and how what you got there. So I start with an introduction question that Aaron designed, which is how do you get interested in this particular topic to get us all started? What got you onto this?
Yeah, I mean, that's a fantastic question to ask and kind of to begin, the introduction. And I actually got into astronomy, like as a kid, I was very interested in astronomy, but I never actually saw an astronomer. I was back in India. I didn't see someone with a career in astronomy before me until I was in my third year of undergrad. So I was doing my like BSc, like bachelor's in physics back in India, and then there was a, a, a handful of professors who joined the department who were all astronomers, and we used to have like chats about careers, about what astronomy is, what astronomy career looks like. Um, then and I got really fascinated and I started, doing some research project with one of them, and that really got me intrigued. So I really got in astronomy pretty late. So I didn't know what someone does actually when I was like, let's say, first year undergrad. So yeah, so after completing my bachelor's, my undergrad, I moved to the US. I joined UC Santa Cruz as a grad student. I completed my PhD in 2022. And then I went to Johns Hopkins for my first postdoc. And last August, as of last August, I am in Arizona State University. So yeah, that has been my career trajectory until now.
So, and how did you get into fountains and jets and black holes? How did that happen?
Believe it or not, I have worked on I have worked on solar flares, on accretion disk theory, on blazars. But one of the things that really intrigued me was black holes because who is not interested about black holes? So yeah, so one of my first project was actually in blazars. So it was more like time variability and how the kind of the optical and gamma rays kind of is variable over time because of the black hole emission mechanism. So it was not directly black hole, but it was kind of still looking at the emission along the jet. So I was very interested, but then I kind of in PhD, I talked to a few people and I was doing a lot of projects, but this one, like the ones that was kind of more geared towards black hole galaxy coevolution really interested me the most. So I kind of moved slowly towards that, but along with this topic that I'm speaking of, I also work on like high redshift galaxies, epoch of reionization, Lyman alpha, Lyman continuum escape. So those topics are still there. So I work on those as well. But I would say this is the one that is closest to my heart. So when I give a talk, I kind of make this as the main theme of my talk. But if you're interested to hear about other things regarding galaxies or the universe. I'm happy to chat about that as well.
With that, let's hear from it. Let's take it away.
Sounds good. And do you see this in presentation mode?
Yes. Oh, good.
Okay, sounds good. Sounds good. Let me hide my floating meeting controls. Okay. All right. Thank you so much. And hi, everyone. Thank you for being here. So I'm Namrata Roy, and today I'm going to talk about active black holes or active galactic nuclei, particularly how they shape the galactic gas across cosmic time. Mhm. But before I kind of jump onto that topic, let me start by asking the question that we as scientists are ultimately trying to answer. That is, how did we get here? And of course, after decades of work, we now know that the universe started with the Big Bang, and then it was followed by a series of events right after it that ultimately led to the beginning of the first set of stars and galaxies after a few 100 million years. And if you look at the galaxies today in the current epoch, you will see that the universe is actually made up of a mixed bag of galaxies, really. There are different shapes, different morphology, different types of galaxies. So, in between these first galaxies that emerged after a few 100 million years and today's universe, there is of course, about 13 billion years of evolution. So the earliest galaxies look nothing like the galaxies that we see today, and there is a reason. There has been so many years of evolution in between. So we really need to understand this process of galaxy evolution to be able to answer the question, how did we get here? And this is really the perfect time to answer that, to try to answer that question, because we are blessed with so many big and powerful telescopes that are working right now across the wavelength regime. So the Hubble Space Telescope has been really groundbreaking in terms of looking at galaxies nearby, but also galaxies far, far away from us. So here on the left-hand side, you are looking at the image taken by Hubble of a very small patch of the sky. So this is only a few arc minutes by few arc minutes. But within even this very small patch, you can see there are so many galaxies. It's filled with small dots, each of which is a galaxy. And they have, like, you can already see this kind of stunning variation in the morphology, the types, the shapes of galaxies. But now we have a bigger and more powerful telescope up in space, as everyone knows, the James Webb Space Telescope. And James Webb has taken the picture of the same part of the sky. And you can see that this picture, the picture on the right, is way deeper, way more sensitive, and way sharper. And it kind of picks out way more faint dots in the image that Hubble couldn't pick up. So it can look at galaxies much far, far away from us. So we are really looking at farther and farther galaxies back in time. And there are possibly about several tens of thousands of galaxies in this small patch of the sky. And it's always exciting. I spend a lot of time just kind of marveling at these images and trying to look for the small dots and blips that you can barely see. Uh, just, just to give you an example, there is this one small dot that you can barely see in the image, but this is actually a galaxy at redshift 8.5. And this is actually one of the earliest high redshift galaxy that JWST looked at with its first deep image that it took. But then, since the launch of GWST, it has been breaking records every single month. So after 2022, there was galaxies that we are discovering routinely at redshift 10, redshift 12, redshift 14. So currently, the record holder of the farthest known galaxies at redshift 14, 14.3. And so our understanding of how and when the first galaxies emerged have already changed, and we have already started to push back to some of the earliest known galaxies that we know of using this fascinating instrument, this fascinating telescope. And not only just looking at these high redshift galaxies, we are also really peering deep into the details of some of the closest galaxies that we have around us. For example, this is a picture of the phantom galaxy where you can really resolve the spiral arms, the dust, and the star-forming clumps along the spiral structure using JWST. And as I said, between these kind of first set of galaxies that emerged and the galaxies today at redshift 0, there is almost 13 billion years of evolution. So this is really a big journey that the galaxies underwent through to be able to look at the galaxies today, like Milky Way and Andromeda. So when we take optical images, we mostly look at the stars, but galaxies do not just look like blobs of stars, right? Galaxies actually look something like this. So here I'm showing a video or an animation from a cosmological simulation, large volume cosmological simulation, TNG50. And this is basically showing how gas is kind of moving through these cosmological filaments and settling in the center of these massive dark matter halos. And they are kind of coming together and they're triggering star formation. And here this small panel is showing how the stars are being formed at the center, which is generally what you see in optical images. But this is this invisible part, this invisible baryons, where we have this wave of gas, diffuse gas in and around galaxies. And that is really where most of the action happens, right? This gas gets flung out, they are reaccreted back. They form the place where majority of outflows, recycle, everything happens. So really, in order to understand how galaxies evolve, how galaxies were formed, how galaxies die, we need to really understand the gas in galaxies along with the star formation properties. So we know that gas is the fuel for star formation. When there is gas, there is star formation. When there is not a lot of gas in the galaxy, that means there is no star formation. So if we just have gas under gravity, would that form a realistic galaxy? Would that ultimately solve all our problems? Does that mean that we know everything about galaxy evolution? So gas means star formation, no gas means fuel. Absolutely not. This is absolutely not the whole story because, as I showed before in the simulations, if you put just gas kind of flowing in and forming stars and coming together under gravity, that will not form realistic universe. Why? So let me show you with an example. So in the y-axis here, I'm plotting how much new stars are forming in the universe per unit volume, per unit time. And then in the x-axis, I have time. So time since the Big Bang. So zero, around zero is the early universe, right after Big Bang. And then here is the current universe. So here, what we do is we take those simulations, similar simulations that I showed before, and then we plot how much new stars are forming per unit volume over time. And this is what we see from the simulations if you just have gas flowing in under gravity and forming stars. So here in the simulations, what happens is the amount of new stars that are forming, the rate of new stars increases steeply in the early universe because you have a lot of gas to produce a lot of stars. But then after a certain amount of time, they kind of become constant and they kind of become saturated. But then if you go and observe this quantity, how much new stars are actually forming in our universe, we'll see the data to look something like this. So there is a huge mismatch between the simulations and the data. Particularly, the simulations are producing way too many stars compared to what we are actually seeing in the universe. So that was a fascinating challenge back in like early 2000s. And the simulators, the theorists found out that if in their simulations, they put an energy source, particularly an active black hole, actively accreting supermassive black hole, then the simulated universe or the rate of forming stars actually matches pretty well with what we see in the data. So you can see the red line mostly goes to the data now. And then, but then why is that, right? So why putting an active black hole changed the simulation output so much? That is because when you put a black hole in these simulations, they don't sit quietly. So they blow stuff out. They turn on active. They can blow stuff out. They can heat the gas. They can also ionize the gas around it. So that basically gets in the way of these gas forming stars. So the rate of star formation kind of declines because of that. So that's why the simulations could account for this kind of mismatch. And it has been found that you need, in order for these black hole driven energy to drive significant impact, you need something of the order of like 100 trillion times that of the solar energy. So you need a huge amount of energy to be able to escape from this active black holes, or also called active galactic nuclei. But that if you can somehow incorporate that energy into the baryons, then you will be able to kind of account for this mismatch. So this process, as has been suggested by simulators, it's called feedback, or active galactic nuclei driven feedback. And this has been, has been incorporated in simulations since, as I said, about 2000s or so. Okay, so let me take a step back and revise what galaxies look like, right? So galaxies are not just stars. They have this huge amount of gas and dust, as I showed in the simulations. They have this dense gas, the interstellar medium, but they also have this kind of large reservoir of diffuse gas called circumgalactic medium all around it. And every galaxy has a supermassive black hole in the center. And when they turn on, then they're called active galactic nuclei. And simulators are telling us that this active galactic nuclei can cause a huge impact on the galaxy's gas and how they kind of shape and mold the galaxy. So the gas and energy cycle between these different components in a galaxy ultimately shape what a galaxy looks like. But remember, these are all from models, right? So we have learned that AGN might impact galaxies, or AGN might have a significant impact on the gas from different kinds of simulations. So that is where we as observers step in. So I'm an observer. So my job is to really constrain, or to be able to give a number that how much of these black hole or active galactic nuclei energy actually transfer to the surrounding region. So how much energy, momentum, mass gets flung out from this AGNs to the surrounding gaseous reservoir, and how does that energetics shape the star formation? And I talked about this mismatch. How does that shape the baryons, the gas reservoir itself, but also how much star formation is happening in the host galaxies, and how that is shaped by these active galactic nuclei? And then finally, how does that process change over the cosmic history of the universe? So we have these earliest galaxies, and we also have these kind of present day galaxies that look very different. So how does that effect of feedback, active galactic feedback, change how the galaxies evolve? So I will try to kind of answer these three questions, and by showing different kinds of observations of AGNs and their host galaxies. And I will start with radio galaxies. Why? Because these are one of the most obvious AGNs, and they have this black hole that drive these large-scale relativistic jets on either side, and often these jets kind of end in shocked region called lobes, and these are very luminous in radio. And these radio galaxies can be like giant powerhouses of energy. They have a lot of energy in them. And I will talk about these radio galaxies, but at high redshift, at redshift about 3.5 to 4. So I'll be discussing how these powerful jets driven by these radio galaxies, these jets and lobes, influence the galaxies in the young universe. Okay, so let me start by showing you an example of a radio jetted AGN at redshift 4. So in the left-hand side, I'm showing a radio image. So here you can see these two bright blobs. So these are the two radio lobes on either side. And they are connected by a jet, but this jet is often very faint. And here this is at redshift 4, so these are really hard to see. And the galaxy itself is located here in the cross sign, and that is also undetected in radio. And remember, our goal is to look at how these radio lobes and radio jets impact the galaxy's gas and the star formation. So we need to look at the spectral informations, particularly the emission lines and the continuum, and they all shift to the near infrared, particularly the ones that I'm interested in. So we use the James Webb near spec instrument, particularly the IFU, to look at the gas and the stars in this galaxy. So what we did is we put our galaxy and the bright lobe within our IFU field of view, and this is what we observed. So in the right-hand side, I am showing the spatial distribution of warm ionized gas as probed by the oxygen-3 emitting line. And you can clearly see that the region between the galaxy and these radio lobes, these are not empty. These are actually filled with this extended reservoir of gas, starting from the galaxy all the way up to the radio lobe. So, and they have this really intriguing morphology that is really fascinating. And I just want to kind of say that because I say that all the time in all the talks, is that, a few years back, getting even one spectra from the whole galaxy was a challenge because this was at redshift 4. So now we are kind of resolving how the gas is moving in and around the radio lobes in a radio galaxy at redshift 4. So this is absolutely fascinating. And thanks to JWST, we have these images, we have this information. And these are not images, these are from IFU observations. So we have a spectra from each of these different spaxels, and we extract that information, and then we plot the flux here. So the most exciting thing about this map, the most intriguing result, is that this diffuse extended ionized gas that we are seeing in oxygen-3, it's very strongly aligned with the jet axis. So the jet axis is the line connecting these two radio lobes. And so the ionized gas is very spatially aligned with where the jet axis is. And they are co-spatial with the radio lobes. And we don't have just oxygen-3, we have a ton of other emission lines. So we have sulfur-2, neon-3, neon-5, H-alpha, nitrogen-2, etc. And you can see that all of this emission line probing this ionized gas is actually pretty extended, and they extend all the way up to the radio lobes. They also, of course, have a slightly different morphology because of the ionization states of the gas. But the bottom line here is that there are lots of ionized gas that is co-spatial with these radio lobes. Okay, so let me now talk about how this gas is actually moving around. So in order to look at the kinematics, we look at the emission line profiles because that encodes information of how the gas is moving around. So just to give you some baseline, so if the emission line is narrow and symmetric, that means gas is kind of moving in a coherent bulk motion, moving mostly under gravity in a disk. But if it's broad and asymmetric, it's generally interpreted to be an outflow. So let's see how our galaxy spectra looks like. So in the center of the galaxy, where the main galaxy is, where the stars are, the spectrum of oxygen 3 looks something like this. So here you have a narrow component which traces the coherent motion of the gas, and then on top of that there is a broad component which kind of traces how much gas is the turbulent component of the gas. And you can see that the full width half max is about 700 kilometers per second. So that is a measure of how turbulent or how disturbed the gas is. And 700 kilometers per second is, you can say that the gas is kind of disturbed. So there are a part of the gas that is coming out. But then the interesting thing is when you move more towards the radial lobes, the line profiles become much broader. So now this same oxygen 3 line, you can see that as you move towards the radial lobe, now splits up into these two different components, to two different peaks, and each of these individual components also become very much broad. So the full width half max now shoots up to about 1300 kilometers per second, so about twice the value that it was at the center of the galaxy. So that means the gas becomes way more turbulent, and then there is a larger fraction of the gas that is being ejected out. And as you move more towards the radial lobe, towards the center of the radio contour, you can see the line profiles become even more wacky. So it's really broad, and the lines are really velocity shifted, and they are separated out, and they have really multi-component structure. So it's really hard to model these line profiles because they are so broad and they are so turbulent. So this is a classic sign of gas. As you move out of the galaxy, you have a greater velocity, you have a greater velocity dispersion, and you have much more turbulence. So it's a classic sign of gas that is being ejected out as you move out from the center of the galaxy towards the radial lobes. And you can, of course, plot a map of the width of the line. So I have been talking about full width half max. So here I'm showing the resolved map of this full width half max. And you can see that in the center, the lines are pretty narrow, so it's about 300 to 350 kilometers per second, maybe 400 kilometers per second. But as you move towards the radial lobes, you start getting more than 1,000, 1,500, 2,000 kilometers per second. So the gas is moving comparatively slower and much more coherently near the center, but as you move towards the radial lobes, it's way faster. So the takeaway point here is that these radio jets are ejecting a lot of this ionized gas outwards, and we measure that outflow velocity, and that is somewhere around 800 to 1,000 kilometers per second. So really huge outflow velocity. So I started this talk with this question: how much mass, energy, and momentum is actually deposited by these AGNs is something that we need to constrain. And since from these high redshift radio galaxy, we have all these different kinds of lines, we can measure temperature, density, flux, luminosity, velocity. So we can actually start to constrain with some assumptions how much mass energy is being ejected out. So the mass outflow rate, which is the rate at which mass is being thrown out from the center, is about 500 solar mass per year for this source. So that means there's like a huge amount of mass that is being displaced. And 500 solar mass per year is pretty big. You don't see this kind of number even in very luminous quasars. So that means a huge amount of mass is being pushed out from the center of this galaxy. We can also constrain what is the kinetic power, the kinetic energy per unit time in ionized gas. And for this source, that is coming out to be about 10 to the 44 arc per second. So this is also pretty big. But if you compare that with the amount of energy or the amount of power that is in this black hole jet, so that is actually higher. So the kinetic power in the black hole jet is around 10 to the 47 arc per second. So the number in yellow is the power or the energy in the ionized gas component in these winds. And the number in red is the energy that is in the black hole jet. So if you divide one by the other, you actually get that 0.1% of the jet energy is actually in the warm ionized phase. So what does that mean? That doesn't mean that the feedback is not efficient. It just means that possibly the rest of the energy is in a much hotter phase of the gas stressing a temperature of about million Kelvin. And that has been seen in other observations as well. So it just means that majority of the mass is actually in this warm ionized phase, but majority of the energy is carried by this hot phase. So you can imagine these to be actually like that. So the jet is pushing out and they have this kind of warm ionized gas clouds kind of floating in and around these kind of lobes, which are carrying a lot of the mass, but then the whole thing is embedded within this hot reservoir of gas, which is carrying most of the energy. So this was just one galaxy that I told you about, but we actually have a sample that we'll look at. So these here I'm showing four other redshift 3.5 to 4 radio galaxy. And the images are from the ionized gas as traced by oxygen 3, but these magenta contours are the overplotted radio contours. And you can see in all of these systems, the radio and the ionized gas are very strongly aligned. They are co-spatial. So we have ionized gas along these radio lobes or these radio jets in all the systems. And we obviously look at the detailed kinematics and the energetics in all of the systems. I'm not going through that now. But all of this, we see that all these radio jets are ejecting a lot of ionized gas with mass outflow rate between 100 to 900 solar mass per year. So really huge amount of mass that is being displaced, depending on what object you are looking at. So we can actually plot how much energy that is being flowing out in this ionized gas component as a function of what is the luminosity of the AGN. And here, the gray points show low redshift AGNs compared with our high redshift radio AGNs that we have been talking about in these colored circles or colored symbols. And you can see that the radio AGNs in the younger universe, the ones that I have been talking about, kind of lie on the top of the distribution. So they have the most energetic outflows in the warm ionized phase. So they kind of lie here, while the most of the low redshift AGNs kind of lie on the lower tail of the distribution. And I have been working with a grad student at JHU, and he's actually looking at AGNs across the redshift space, but looking specifically at the AGNs which do not have these large scale jets. And he's trying to see whether those kind of AGNs can also trigger outflows which are this energetic. So stay tuned for those results. So next, I will kind of move on to the second part of my talk is the fact that these really powerful jetted AGNs that I have been talking about, these are short-lived. They are not around for a long time, right? Because they are only there for a few million years. So what happens after that? They eventually evolved to much weaker low luminosity AGNs. And if we want to understand what is the role of these AGNs on a galaxy's lifetime, on the lifetime of galaxies, we must also understand this low luminosity phase of the AGN because they are possibly way more recurrent than these really massive large-scale jetted AGNs. So for that, I'll be talking about these weak AGNs, but since these are weaker signature, low luminosity signatures, these are much harder to actually see or observe. So I'll be talking about them mostly in the nearby universe at redshift 0. So how these weak black holes influence galaxies today. So to talk about this low luminosity AGN, I will mostly discuss this new population of galaxies that we discovered called red geysers. And we discovered this using Manga IFU survey. So this was like a few years back. And what are red geysers? So red geysers are really passive, quenched, old population of galaxies. So if you look at the SDSS images of some of these red geysers, they look something like this on the left. So here you can see the optical image looks extremely elliptical, spheroidal, very normal looking elliptical galaxy. And their stellar population looks very old. So these are old galaxies. They don't have a lot of star formation happening. But when you put on your IFU goggles, you see the distribution of ionized gas looks something like this. So here I am showing the spatial distribution of H alpha emitting gas. And you can clearly see that the gas is kind of widespread. So the scale of the image is about 10 to 15 kpc. And you can see that there is ionized gas extending all the way up to the Manga field of view over tens of kpc. And not only that, they have this weird bisymmetric or biconical morphology. that is really apparently visible. And this is actually one of the main intriguing signatures of red geysers, that they have these really large scale biconical structures in the ionized gas. So we call these red geysers because these are red and dead. So there is not a lot of star formation that is happening. And also because their ionized gas looks like a geyser or a fountain. And these red geysers, these are not a few galaxies that we are talking about. There is actually, they account for actually 10% of nearby quenched galaxies that we looked at with Manga's IFU survey. So they are actually like a sample, a really big sample of red geysers that exist. So the question that we asked is, what is this widespread ionized gas doing? So are these biconical features tracing gas that is being ejected out, something like this, like a wind cone where you have a near and the far side of the bicone and gas is being kind of ejected out? So to test that, whether these are actually black holes driving winds, if these are actually winds, we look at the emission line profiles again. So this is the expectation of the line profile. So if you are looking at a cone, a bicone at a certain angle, and you are looking at the near and the far side, the line profiles will be asymmetric and broad, but it also, the asymmetry should switch from one side to the other because of the geometry. And so then I went and looked for high spectral resolution spectra using Keck to be able to see whether the line profiles look something like this. And this is exactly what we see. So here I'm showing the observed spectra, and you can see that the observed spectra is exactly like what we predicted from our wind model. And you see the line profiles are asymmetric, but not only that, the asymmetry kind of switches from one side to the other. So there is a blue wing, and then there is a red wing when you go from one side to the other. So we did some detailed modeling, and we took different observations across the galaxy, and we confirmed that these are really low velocity winds extending to about 10 kpc. And the velocity of these winds are much more gentle. So these are like 300 kilometer per second winds, as opposed to those 1,000 kilometer per second winds I was talking about before. So these are much low velocity winds, but still these galaxies are driving this gas that is being ejected out in this bicone fashion. So then, of course, what is causing this wind? So we wanted to search whether they have an AGN in the center. So we looked at the different radio surveys. So we cross-matched with FIRST, VLAS, and LOFAR. And surprisingly, we found that the centers of these red geysers have radio AGNs. And they have a wide range of morphology. In some cases, they have compact radio. Some cases they have this kind of extended two-lobed structure. In some cases they have a full-blown jet, which is really large scale. So we find that they have really a mixed bag of radio morphology in them. And then we plotted the radio luminosity with star formation rate. And we find that our red geysers, they're all consistent with AGN, but they are much lower luminosity than these powerful radio galaxies I was talking about. So the powerful radio galaxies lie somewhere above this, and our red geysers, they kind of just graze the separation between the AGN and the star formation. So these are all coming from AGNs, but these are very low luminosity AGNs that we are looking at. So the main takeaway point here is that geysers, these red geysers, they host faint weak AGNs with both compact and extended jet morphology. And these AGNs, these weak AGNs, are possibly driving this kind of centrally driven winds that we are seeing in this ionized gas. The final kind of result I want to talk about these red geysers is what is feeding those AGNs, right? So we are seeing these weak AGNs kind of turning on and driving these winds. So what is causing them? What is feeding them and turning them active? So for that, we actually look at the cooler neutral gas in absorption. So I have a student working with me, Aryan, who just submitted this paper and he got a referee report. So long we have been talking about this ionized gas in emission, where we see this bisymmetric or a biconical outflow. But now Aryan is looking at the cooler neutral gas in sodium D absorption line. And when he plots the depth of the sodium D absorption in the map, we are seeing that this cooler gas, the morphology of this cool gas looks nothing like this ionized gas morphology that I've been talking about. So they look very one-sided, very kind of compact, and kind of very directional. So then what Aryan did is he modeled the kinematics of this sodium D. And what he found is that majority of the sodium D emitting this cool gas is actually inflowing rather than outflowing. So what is happening is that this neutral gas, the sodium D gas, is actually coming in from one side and connecting the center. And we actually do found a correlation between the rate of infalling gas and the presence of radio observations of the central AGN. So there is, we think, is a very prominent connection between this infalling gas and the radioactivity of the AGN. So these cold gas is possibly raining down to fuel some of these weak AGNs. And we measured the inflow velocity, it's somewhere around 50 to 60 kilometer per second, and that is consistent with what you expect at these distances. So just to summarize what we know about red geysers is that these are mostly elliptical or spheroidal galaxies. These are quenched, not a lot of star formation is happening, so they have mostly old stars. The black holes, they are active, but these are weak. They might have a small scale jet, and they kind of drive these large scale gas outflows in this ionized gas. A part of the gas might escape completely, a part of the gas might come back down, and we do detect signatures of infalling cooler gas. And they might originate from this recycled kind of fountain, or they can be freshly accreted from outside. Here I'm just showing all these different papers that we wrote to kind of have this picture of gas cycle in red geysers. And really the interesting part about red geysers is this was kind of one of the first generation of like quiescent galaxies with outflows that we discovered. And now with JWST, we are seeing outflows in quenched galaxies all the time, all the way up to redshift 2, redshift 3. So this has been really one of the earliest population of galaxies that quenched galaxies with outflows that we discovered. And so these are very exciting to study. Okay, kind of in the last 2-3 minutes, I will now briefly talk about the fact that these red geysers and the giant radio galaxies that I talked about still are only account for 5 to 10% of the galaxies with AGNs. So what happens to the rest of the galaxies? We know there are quasars, but they are also pretty rare. So what about the rest of the galaxies? Do they not host AGNs? Or if we look deeper enough, we would find AGNs in many of them. So to answer that question, to actually know the abundance of AGNs, weaker AGNs in galaxies, I have been taking this new spectroscopy technique called slit stepping. So what we are doing is we are placing the JWST slits, here on the left-hand side, I'm showing the slits, multiple slits on top of many galaxies in the same field. And then we are dithering and scanning the telescope in a clever way so that we get resolved information from each of those galaxies, and we get a pseudo IFU cube. So we get resolved maps of fluxes and velocities and dispersions, something like this on the right-hand side. So the major benefit for this is that we can get spatially resolved spectra for multiple galaxies at the same time. So for this program, MSA3D, we were targeting redshift 1, but we can do this for any redshift. And instead of going one galaxy at a time in the IFU mode, we can actually do this kind of resolved study for a survey, more like a survey mode, where we can observe many galaxies at the same time. And this is particularly useful because we are trying to kind of really use the spatial resolved information to understand if there are hidden AGNs or hidden outflows that we are kind of missing when we are using integrated survey or observations. So here we did find that majority of the galaxies which look like star forming disk galaxies, nothing special is happening to them. When we look at the resolved dispersion, the kinematic maps, the velocity, the dispersion, the BPT and WAN diagram in the spaxel level, we are actually seeing broad asymmetric lines. We are seeing Seifert-like ionization. We are seeing enhanced velocities and dispersion. And we find, and these are just some examples, I'm not going to spend some time on this, but the main result that we find is that about 16% of redshift 1 star forming main sequence galaxies, which do not have any AGN and outflow or quasar signature in their integrated spectra, actually host hidden outflows and AGNs when you kind of split them up with IFU. So this is really fascinating because these are help us understand what is all the information that we're missing, and this would be fascinating to kind of follow up with IFUs. So I have been mostly talking about ISM, But one of the things that I'm most excited about in the next few years is connecting these ISM observations with kind of the larger scale CGM gas around some of these AGNs. So I talked about these radio galaxies, these giant radio galaxies. So one of the new programs that I'm leading with HST is called COSRAG. So this HST program was accepted recently. So our goal here is to look at the extended CGM around the radio lobes of some of some of the nearby radio galaxies in absorption using HST. So what we will do is we picked background quasars and with foreground these extended radio lobes, and we are looking at the gas in absorption. We expect to see lots of different excitation, different ionization lines across ionization scale. And this will be really fascinating because then we can kind of compare these pencil beam absorption tracing the CGM with our extended ISM observations that we already have. And the next step obviously is HWO, because then if we have a UVIQ in space, we would be able to map the CGM in emission. And that would be fascinating because we can move on from pencil beam observations to more kind of resolving the diffuse structures in the CGM. And all these different lines would be able to give us the range of temperature and density of the gas, can help us resolve this multi-phase, multi-structure gas in the extended CGM. Because the CGM is where a lot of the gas and the energy actually is entrapped, right? So we have to look at both the ISM and the CGM to be able to have the full picture of the energy and the momentum and the mass that these AGNs deposit. So yeah, I'm really looking forward to HWO and what that kind of unfolds after a decade, in the next decade. So yeah, so hopefully I was able to kind of answer some of these questions that I laid out in the beginning of my talk. And I'm really excited for the future and what NASA does, and happy to take questions. Thank you so much.
Hi, this is Ozzy. Wonderful. Thank you so much. Yeah, so open to the room for questions. Either raise a hand or, well, start with raising hands, or if that doesn't happen, see if somebody wants to jump in. Jason. You're muted, Jason, or very, very quiet.
Can you hear me now?
Yes,
Yeah.
much better.
All right. Fascinating talk.
Thank you.
I'm interested in the sodium D line absorption. So when you make that observation, how do you distinguish between absorption in the ISM and the underlying stellar absorption?
Yes, yes. So we modeled the ISM. We tried with 3 different templates. So there is one that is specifically designed for manga. It's called Master. So it was developed by Renminian. So we used that to kind of do the stellar modeling. But before that, we also tried different other templates like BPAS, and then we compared how much ISM difference we are getting. So the difference due to choosing a different stellar modeling is only like 5%. So we accounted that error inside. So what I'm showing you here in this plot is the continuum subtracted, continuum normalized ISM on the sodium. Yes, we do have to account for that because these are kind of older stellar populations. So you'd expect sodium D from stars as well. So that's a great question. So we did spend a whole bit of time kind of making that modeling. Yeah, yeah.
Can I ask one more question? I'm really curious about that plot where you showed kinetic energy versus AGN luminosity. It was kind of maybe 10 slides back.
Yeah.
So your objects have a higher AGN luminosity and a higher kinetic energy, gas-phase kinetic energy than low redshift objects.
Yeah.
But aside from the fact that they're higher on both axes, they do seem kind of in line with what we see for low redshift objects. So is it that the AGNs at Z of 4 are on average more energetic, but other than that, like the way they live in their
Mm-hmm.
galaxies is kind of the same?
Yeah, that's again like a really good question and really good point. And yeah, so that's something that fascinated me as well. Like how they kind of still kind of fall on this diagram. So we don't know, right? So maybe like the fraction of energy that the AGNs can deposit can only be of like zero point 0.1 to maybe like zero point 0.5 or something. So maybe that fraction is kind of constant
Yeah.
over the whole axis because we are only looking at the warm ionized phase. So my takeaway point here is that whether irrespective of what kind of AGN you are over the whole redshift scale, the fraction that we are kind of catching in this warm ionized phase is roughly the same. So that's why they are kind of falling on this straight line. So majority of this energy must be in the other phases. Maybe in the CGM, we are kind of missing
Yeah.
some of that. Maybe in the X-ray gas, like million Kelvin gas, or maybe in the colder gas, right? So if you just take the ionized component, that fraction of zero point 0.1 to zero point 0.5 is what they're all lying on. So that is, I agree, that's very fascinating. And I had a plot, I removed that because of time constraint. I had a plot with the red geysers and all these different samples overplotted on this, and they are all kind of aligned with this line. So this is,
Really?
yeah, yeah.
That's cool because it's a totally different kind of object.
Right. And those red geysers,
Oh,
they are very in the lower regime. So they are
yeah.
kind of around 10 to the 40, but they are still consistent with this line. So if you draw a line, they mostly fall within this scatter. So maybe the fraction of energy that these AGNs can translate is remaining roughly constant. So that's something that is very fascinating. Yeah.
Thank you very much.
I have a question here in the notes. Do we see entrainment of other phases of gas other than ionized in jets, such as warm, cold, molecular, or neutral gas? Which
Yeah. So are you talking about like the radio galaxies, like these large scale jets, or the red geysers? I'm assuming radio jets, like the first part.
the radio jets? Yes, I think that's the radio
Yeah,
jets.
yeah. So, like, this is something that I want to do is have like a normal proposal to get like molecular gas. Um, but I would expect that, I mean, molecular gas, for example, outflows are much harder to detect. Those are way more kind of, they are way more kind of disky. They look like disks. They have much more coherent motion rather than those large scale outflows. But still, we want to kind of look whether CO. In the whole sample, we do have, like, there are some CO observations made by Yuji Wang, and he did see CO clumps along this different jets. So there are CO. We just have to do a more kind of careful job of, looking at the CO systematically across the whole sample. So that's something that um, we have to do. But there are CO observations uh, in and around those kind of radio jets lobes that I showed.
Okay, I have a question from Patricia Fuffy.
Yes, hi. Thank you
Hi.
for this. Hi, fantastic talk. This was very interesting. I do mostly simulations of AGN feedback and galaxy
Mm-hmm.
morphology. So talking about
Mm-hmm.
radio jets and that is very like pertinent.
Uh-huh.
I do want to know, you mentioned that the red geysers are about 10% of the quenched population. Do you
Yeah.
know if they have a preference for the morphology that they're in, whether it's more elliptical or lenticular of the quenched population that we're
Yeah.
seeing geysers?
These are all mostly spheroidal looking. There are a few maybe slightly disky, maybe slightly has an inclination or like you can see like a bit of like a diskiness, but majority, I would say 90%, around 90% are actually elliptical. And if you just look at the SDSS images, I did that exercise. So I looked at the SDSS images and I looked at a bunch of other SDSS images and see if I can pick out red geysers. You can't pick out red geysers. So these are very normal looking elliptical galaxies. They look like they're quenched. If you just look at their integrated spectrum, for example, from SDSS, they look like just old stellar population with some emission lines. So
Mm.
they look like a liner in the integrated spectrum. And that's why over several years, these kind of objects were looked like they were kind of overlooked because, you just look at liners, imagine, okay, that's an old galaxy with maybe some gas. But then when you have outflows, when you have IFUs, you can kind of go back and then you can look at this. And we did also actually looked at some of the earlier IFU surveys like SAMI and Khalifa, and we found that these kind of objects existed there as well. People just didn't know what they were, and they just, said that, okay, these are just weird objects.
Interesting. Interesting. Thank you.
Excellent
Yeah.
question. Okay, who else has a question? Do I see hands? Do I see otherwise I have a follow-up about the red geysers, which is that you see cold gas fall in, and then you would expect that it would self-collide at some point. So you expect some level of star formation in there, right? So would you expect some blue light or from frosting in these galaxies?
Okay, I'm curious because you said like collision. So we calculated something like a drag force, like if the gas is kind of falling in, how much drag force it would encounter. But that calculation didn't go much further. But these are neutral gas, so these cannot trigger star formation yet, right? So you need to have molecular gas. So we tried to look for molecular gas with single dish observations. We didn't find any molecular gas. So possibly these winds are keeping the gas from, forming this dense molecular gas of 10 Kelvin temperature. And maybe that's why we're not seeing the star formation. So there is ionized gas, there is neutral gas, but there is not molecular gas yet. So maybe when the winds maybe turn off, or maybe the AGN can go quiet, maybe those can form molecular gas and trigger some star formation in the future, but not yet. We didn't find any molecular gas yet.
I have a question from Nick Prusinski.
Yeah, this is all very interesting. I just wanted to ask on your COS-RAD survey, your HST survey,
Yeah,
how many sight lines are you getting and at what projected distances?
these are all like one sightline per galaxy. We had
Okay.
like a sample of like 6, 7.
Oh, okay. Okay.
Yeah, it's just like one sightline per galaxy. These are actually really hard to get because we were constrained. So how I designed the experiment is that your sightline has to cross this kind of radial lobe, right? So it has to be a certain distance, it has to be at a certain angle to be able to kind of probe or peer through that lobe. So that really, takes away your sample size. So we didn't have a lot
Hmm.
to observe. So yeah.
That'll be very interesting to see.
Yeah, we are interested as well. Let's see how the data looks like.
Mhm.
Okay, so quick. Do I have more questions? Mm, I did have one of my own, which was the lifetime. You mentioned that the jetted AGN have about a mega year lifetime, and that's sort of something that we're interested in, or was that sort of a order of
I guess
magnitude guess?
Yeah, I mean, I guess a few million years to like maybe it can go up to like 100 million years, depending on the jet lifetime. But like yeah, I mean the jet, as far as I know, it's like in the order of like a few million years. But of course, the jet lifetimes varies depending on how dense the gas around it is, how powerful the jet is, how far out, where at what time we are catching them, right? So um, there is a lot of, I guess, scatter in that. But yeah, that
Uh,
was more like a very rough quote.
okay, I was just curious if you start having a timer on it, when AGN switch off and when they like lifetime of AGN activity, because that you keep finding them in various strong line mapping, for example, like you did with the slit stepping. Um, so it is a bit, are all agents just on, but at various levels? And so that's feel free
That's
to speculate there.
that's the question, right? So one of the question that motivated this kind of like resolve large scale surveys is to find how many more can we find, right? So is it just they are there, we are not looking deep enough, or we are not resolving them, so it's just all messed up in the integrated and it's not visible. If you have a star forming disk, the star formation is dominating the ionization, it's dominating everything. There is a lot of stars, so it's kind of hard to see kind of through that. So that was the idea. And the slit stepping survey that I showed, like we actually have more data coming in, Redshift 2, Redshift 3, from the next kind of JWST cycles. And I'm interested to kind of see how many more do we find, because um, like the sample that we have, these are star forming main sequence galaxies, and these were chosen to not have AGN. So these were very like disky galaxies, only star formation, nothing else.
Yep.
And even then, we are getting more than 10%, 16% with some sort of like outflow signature or AGN or broad line or something. So that's kind of, that's the speculation part. We don't know like whether the AGNs are there all the time, or they can turn on and off, right? So that will account for some as well. But how many actually are there on right now? So I guess that's something that hopefully this kind of surveys, the slit stepping surveys are really efficient in doing something like an IFU, but for a large sample. So hopefully this kind of surveys will, answer this question eventually in the next few years with JWST.
Nice. Yeah, it always feels like there's a 10% is an AGN, but it's not. It's a different 10% every time.
Yeah,
So,
exactly.
um,
That's exactly what my slide said, right? There's a
yeah,
10%,
exactly.
there is a 10%,
Yeah,
there is another
another 10.
10%. Yeah.
So, okay, because that's something that we keep running into with OH mega majors, for example. So it's another one. Is that is a hint
Mm,
of an AGN or not?
mm,
I also noticed that a lot of them were like you said, the ellipticals were morphological. Like that's undistinguishable from an elliptical. That means that you have fueling mechanisms other than the canonical merger, because
hmm.
that's what it says in baby astronomy. It's grad school astronomy
Right.
101. Here's, the AGN switch off on because you have a merger going on. But you showed at least one where that's not the case. It feels like it's all of them.
Yeah, I mean, they might have gone through some sort of tidal interaction in the past. Like in some cases, in some of the images, when you look at like high resolution images, you seem to show some kind of like shells in some of them, like
Okay.
shells or maybe some sort of asymmetry, but they are all ellipticals. It's just like when you look deep enough. But then I heard somewhere that, if you look deep enough in many of these elliptical galaxies, they seem to show like
This,
shells. So
yeah,
I don't know if those are special.
yeah. Everything had a merger, I guess.
Yeah,
Okay,
right,
that's
right. Yeah.
if you wait long enough. Okay, that was my questions. Are there any other from the room? Otherwise, we're at the hour. Otherwise, nicely timed by
Thank you for all
everyone.
this. Yeah, thank you for all these amazing questions.
Thank you for a
Yeah,
great talk. That was fun. All
thank
right.
you.
Um, yeah,
Thank you.
wonderful.
Thank you so
Other than
much.
that, see you all
All
next
right.
time. I'll stop the
Bye.
recording.